If we apply a load to a beam, it will deform by bending. This generates internal stresses, which can be represented by a shear force acting in the vertical direction and a bending moment. The shear force is the resultant of vertical shear stresses, which act parallel to the cross-section, and the bending moment is the resultant of normal stresses, called bending stresses, which act perpendicular to the cross-section. It's important to have a good understanding of these stresses because any design or analysis of a beam will involve calculating them. Let's look at bending stresses first. To keep things simple, we'll consider a case of pure bending. A section of a beam is said to be in a state of pure bending when the shear force along it is equal to 0, and so there is a constant bending moment along its length, like there is for this beam, loaded by 2 moments. We also have a case of pure bending over the middle section of this beam, where the bending moment is constant. Let's look at how a beam deflects when it has a constant bending moment along its length. If we imagine the beam as a collection of very small fibers, as the beam deflects, the fibers at the top of the beam get shorter, meaning that they are in compression, and those at the bottom of the beam get longer, so they are in tension. Somewhere between the top and the bottom of the cross-section, there will be a surface containing fibers which stay the exact same length. This is called the neutral surface. It passes through the centroid of the cross-section. When looking at the beam in 2 dimensions, we refer to it as the neutral axis. Let's try and quantify the bending stresses that develop within the beam to resist these applied moments. First, let's calculate the strains in the beam. This can be done quite easily just by considering the geometry of the deformation. Let's watch how a fiber at the neutral axis between points A and B and a fiber between points C and D located at a distance y from the neutral axis deform. Since this is a case of pure bending, we can see that the fibers bend into a perfectly circular arc. We'll call the center of the circle O. Before any deformation, the fibers are all the same length. After the deformation, the length of the neutral axis has stayed the same, but the length of the fiber between points C and D has increased. If theta is the angle of the arc and r is the radius of the arc to the neutral axis, we can calculate the length of the arc between A and B